industry is important today, but the winning of coal and the conveyance of it to the surface has become the most important of all, the prime source of the nation's energy. 50 years ago, all coal had to be loaded into tubs away by men or children or ponies. Today, by a series of electrically or compressed air-driven belts, it can be mechanically conveyed from the face to the pit bottom, sometimes to the light. For the last stage of the journey, the coal pours from the gate conveyor, which has brought it from the face, on to the long trunk conveyor. This is a permanent installation, an endless belt, its joints vulcanized underground. Besides the waste stone brought out of the mine, it carries 300 tons of coal an hour up the 500-yard gradient of 1 in 6. The driving head, appropriately known as the Super Goliath, is powered by an electric motor, in this case of 75 horsepower. Since the weight of coal on the belt varies from minute to minute, it is desirable also to vary the length of the conveyor so that the tension in the belt remains constant. A simple belt take-up, operated by gravity, automatically adjusts the length of the conveyor as the load varies. The life of the belt is thus very considerably increased. At a loading point halfway up the climb, the coal flows from one conveyor to another. To cushion the heavy impact on the belt, the idlers or rollers under the loading point are of a large diameter, coated thickly with rubber. This prevents damage to the belt by heavy pieces of stone or coal, reduces breakage of coal, airborne dust and spillage. At the top of the climb, the conveyor ends with a loading point. Here the coal pours steadily into tubs which run off by gravity to the pit bottom, 7 or 8 a minute at peak period. The full tubs are then raised to the surface in cages by a steam winding engine. In some mines, the conveyors take the coal, and on occasions the coal miners, all the way from the face to the surface. This development was forecast by their inventor in 1905, even before the installation of the first underground belt conveyor. The experiment was first tried at a small mine in the West Yorkshire coalfields. The last conveyor runs up through an open field, screened by asbestos sheeting from wind and rain. At the bottom of the field there is a square brick house. Inside this is the last transfer point, where the coal first sees the light of day. Here one man controls the whole conveyor system. The 2 trunk conveyors, connected by transfer chutes, bring up 300 tons of coal a day and occupy only 3 men in the process between the coal face itself and the screening plant. The journey from the face to surface here involves a vertical lift of 210 feet, a relatively small figure, but since this beginning, much deeper seams have been similarly worked. These conveyors have helped this mine to reach an output per man of more than twice the average for the whole country, in spite of a thin seam and poor working conditions. The last conveyor brings the coal up under the roadway and climbs to the screening sheds. The coal pours down a chute onto the perforated screens, where it is sorted into sizes and the large dirt picked out. The underground belt conveyor is a British invention. Its inventor, Richard Sutcliffe, was an Irish mining engineer. In 1905, he settled in Horbury near Wakefield, and there started the works which bear his name today. In 1905, it did not seem possible that a belt conveyor could be installed and worked underground, but Richard Sutcliffe knew that it could. He made his offices in a row of cottages and his workshop in a weaving shed, the sawtooth roof of which still stands today. There, Richard Sutcliffe and a handful of men produced the first underground belt conveyor in the world. Today, though with different machines and more men, the work still goes on. Here, for instance, is a battery of capstan lathes turning out spindles for the rollers on which the belt runs. Each is accurate to 1/2 of a thousandth of an inch. The center lathes turn shafts for the larger conveyors. Pegs for conveyor framework. These lathes are automatic, at work for 20 hours a day. The operator, who looks after a battery, sets the machine and feeds in a new bar every hour and a half. The rest is done by the lathe. On an assembly line, the rollers are put together. First, the tubing is cut to length. Next, the tubes are wheeled off to join the spindles and end discs, which have already been machined and packed with grease. On a press, the tubing, the spindles, and the end discs are married. All rollers run on precision ball bearings to reduce wear and tear to a minimum. Rollers which have to operate under particularly bad conditions can be lubricated on the spot by grease gun. The end discs are secured by pegs, hand hammered. When they are finished, the rollers go to a number 2 works to be assembled into conveyor framework. Besides these smaller components, the large castings have to be machined with equal accuracy. The gear side of a conveyor head is set up on the planing machine. This is all electric in operation. The cutting tool is the fastest known, its use made possible by the electrically controlled toolboxes. All production castings are drilled through precision jigs. This ensures accuracy and means that they can easily be changed from one machine to another wherever necessary. But before final drilling, a check has been made to ensure the accuracy of the machining. First with the vernier, then with the micrometer. behind skilled machine work like this, there must of course be organization and planning and experiment. In the drawing office, plans are drawn up to customers' specifications. New problems are tackled, difficulties are discussed. Here, conveyors have been designed for many purposes. A bucket conveyor to carry refuse away from the largest block of flats in Britain. Cask elevators for breweries, elevators for flour mills. Many Sutcliffe conveyors have gone into the mines to play a considerable part in the mechanization which has almost transformed the coal industry in the last 10 years. This increased activity has meant continual expansion. From the row of cottages and the weaving shed, there has grown extension after extension. And with the buildings, the staff has multiplied. Now, when the hooter goes at midday, there are more than 500 people to break for their lunch hour. Some like to go home for lunch. Others prefer to eat their sandwiches in the traditional way, leaning up against their machines with a paper and a pot of tea. The alternative is the canteen. In the stockyards, the raw material is sorted and carried by crane into the assembly sheds. Within, the 12 standard types of conveyor are in continual production. Of these, the largest of all is the 120 horsepower Super Goliath, which we have already seen at work. The first stage is the welding of the huge base plate. The Super Goliath will often deal with the whole output of a mine, working for long distances over heavy gradients. Strength and reliability are the first considerations in its design. While the base plate is welded, other components of the Super Goliath are machined. A gearbox on the planer, a side plate on the borer. When the components have been machined, the base plate can be lowered into position for assembly. Now, part by part, the assembly begins. An unusual feature of this machine is the pressure oil feed to the main bearings and gears with a visual indicator. The rising bubble shows that the oil is circulating. At last, the Super Goliath stands, tested and complete. Now it can be dismantled, crated, and carried almost anywhere in the world. Super Goliaths and other smaller machines will be found working in coal fields all over Britain. Many have gone overseas, to Canada, Spitsbergen, Iraq, Borneo, or like this one, to the coal fields of Malaya. Though Richard Sutcliffe earned the name of pioneer through his work on underground conveyors, Sutcliffe conveyors do not work only in coal mines. They work, for instance, in this coke works, which supplies gas to the steel industries of Sheffield and valuable byproducts to many other industries. The making of gas is a continuous process. For 24 hours a day, the battery of coke ovens is fed by coaling car and kept at a constant temperature. When the coal has no more gas to give, a power-operated ram passes right through the oven, pushing out the burning coke. The coal to feed the ovens is carried in a large bunker, standing 200 feet high. At the height of the Second World War, the very existence of these coke ovens was threatened. It seemed that the flow of gas to Sheffield would be stopped for 12 months or more, unless the flow of coal to the ovens could be restored within 12 days. This seemed an impossibility, but Sutcliffes were given a free hand. Within 12 days they had designed, constructed and installed a temporary conveyor. This climbed from beyond 2 railway tracks to feed the coaling car on top of the ovens. This conveyor worked for 14 months until the new bunker was built and a permanent conveyor installed. The permanent conveyors, enclosed in a steel and asbestos gantry, climb to the top of the bunker in 2 stages. Both are worked from a single point at the bottom, where they occupy the full-time attention of only 1 man. In labour alone, this has meant a saving of more than £2,000 a year. The conveyor is fed by a railway truck. Coal flows from a tippler down a chute, is crushed and blended, and then falls onto the tail end of the first conveyor. The first leg, 482 feet long, climbs to a height of 150 feet. Inside the junction house, the coal changes direction. Now it starts its climb up the second gantry. This is 229 feet long. It climbs at an angle of 18 degrees to a height of 200 feet. This gantry had to be installed in 6 hours to avoid interruption of processing. It was erected complete in 5.5 hours. The second conveyor discharges into the bunker, which in its turn feeds the coaling car, keeping all the ovens continuously burning. In 3 years, the conveyors have carried more than 500,000 tons of coal without failure, renewal, or repair of any part. The original belting shows no signs of wear. Quite a different type of problem was presented by a Yorkshire wool packing factory. Here the girls pack skeins of differently coloured wool into cardboard boxes. Previously they wasted time walking round the racks with boxes. As a result, the firm could not handle the packing of all its orders. This conveyor was specially designed to speed up the process. One of the special features of this conveyor is the use of the return belt to carry the full boxes away for sealing and dispatch. At a transfer point, the boxes tip off onto a second conveyor. Finally, the boxes roll down a gravity section to be sealed. This installation has enabled the company to cut their labour costs by a half. They can now pack 1,000 boxes an hour on their own premises. On the coast of North Wales, near Abergele, limestone is quarried from the cliffs and carried away by boat. Quarrying has been going on in these parts for hundreds of years, but the supply of stone is still far from exhausted. By pick and by charge, the limestone is hewn and blasted from the cliffs. The traditional way of moving stone is by tubs, but this is a slow method which wastes time and energy. At this quarry, tubs are used only over the comparatively short distance between the quarry face and the crushing house. 1940, the tubs between the crushing house and the boats were replaced by a series of 7 belt conveyors. The first 4 of these work all day, taking a continuous stream of limestone to the large bunker, where it is stored up ready for loading. The second of these conveyors passes through a tunnel underneath a main road. Here the stone switches direction. Either it can be poured down a chute into railway wagons, or it can run onto the bunker on the 3rd conveyor. The 4th conveyor goes under a double railway line and rises steeply to the top of the bunker at the shoreward end of the pier. Here the stone is stored in 14 separate hoppers, each holding stone of a different size. The 5th and 6th conveyors lie beneath the bunker, idle, until a boat is ready to be loaded. Beyond the bunker, the last conveyor stretches out to sea, waiting for the boat. When the boat is made fast, the chute is lowered from the head of the conveyor. Now all that is needed is the press of a button. At the beginning of its seaward journey on the last conveyor, the limestone passes over a weighing machine, accurate to a few hundredweights per 100 tons. As the register shows, the main belts, still in first-class order, have carried a total of 540,000 tons since they were installed. This represents a belt cost of only 0.55 pence per ton of limestone carried. Before these conveyors were installed, 30 men loaded 200 tons of limestone in an hour. Now, with the help of the conveyors, 6 men can load stone at the rate of 1,000 tons an hour. This has meant great saving in time, manpower, and money. Most important, the boats, which often had to stand out at sea for 2 high tides or more, can be out and away on the tide that brought them in.